SwayamPrabha. Digital India. Educated India.
Lecture number 38. There are other uses of natural dye apart from textile, and today we will learn how natural dyes can act as acid-base indicator in titrometric reactions. So, it is not only textile where dyeing and printing with natural dyes has been discussed very elaborately. We will today discuss how pH indicators also can be made by using natural dyes. You may recall that in the context of anthocyanin dyes, I had mentioned that these dyes have a kind of a reactivity with acid and base, and they change their color. Now, that was on the context of change of color under different pH, but the same can become an attribute and they can become pH indicators. So, anthocyanins had pH variation and color change from red to blue and blue to red. As the pH was altered, with art of using this dye, rose anthocyanin dye as an acid base indicator was identified. So, this particular lecture is a completely non-textile use of natural dye extract and the rose anthocyanin extract, which we discussed in great details, the structure and the dyeing properties and so on and so forth, has a new role to play in this particular lecture. It will act as a pH indicator. So, you will appreciate that dyes are not just meant for textiles or for coloring leather or making inks and prints, but they also have a different kind of role, and that role is directly related to the structure of the dye. So, let us take a look at rose anthocyanins as acid base indicator, where the rose anthocyanin is one which plays the main role. Now, rose may have many other colorants, but the predominant color is anthocyanin, and it is this anthocyanin which is affected by the change in pH. So, that is what we will learn in today's lecture. What is a pH indicator? Let us first understand that pH and acid base indicator. Let us try to understand a pH indicator is halochromic chemical compound that is added in small amounts to a solution. That means it creates a color. So, the pH that is in the acidity or basicity of a solution can be determined usually, or a pH indicator is a chemical detector for hydronium ion, and that is H3O plus, or hydrogen ion, that is H plus. Now, you must have seen lot of litmus papers which change color in the pH. Similarly, we have different kinds of halochromic chemicals which alter with acidic and basic solution condition. So, the moment we used to dip the litmus paper, it would show the pH of that solution, and there is a ring that comes where different colors are mentioned according to the pH value from 1 to 14, and that is something that is called a litmus paper. And similar to that, is a pH indicator. That means the moment you dip into that, you will be able to know what kind of pH it has, acidic or basic. Natural dyes as natural indicators. Like grape juice, other natural indicators such as litmus, China rose, turmeric, red cabbage, beetroot, etc. can be used as natural acid base indicators. A natural indicator is extracted from the plant and used to determine a substance as acid or base. A natural indicator may not accurately provide the pH value. So, it gives an approximation. It does not give you the exact value as what the litmus paper provides. Alizarin or 1,2-dihydroxyanthraquinone C14H8O4 is a natural dye, and as an anthraquinone compound exhibit color change at different pH from yellow in acidic condition to red in basic condition, even that can be used as pH indicator. This range of color changes would propose alizarin, a natural dye, as indicator fabrication. Which dye can be a good model to be pH indicator? Can all the dyes be used as indicators, or are there very specific pH sensitive dyes which can act as pH indicators? Now, let us try to understand that. For making a pH indicator, one must have a reversible nature. That means the protonation and the deprotonation must occur at the required acidic or basic condition. It can also be said that pH indicator changes color depending on whether they donate or accept proton. Now, this has to be a reversible reaction. I gave you an example earlier in the case of sapanwood, where the brazilin was getting converted into braziliine. Now, that was not by acid or base conversion. So, it was a permanent conversion from brazilin to braziliine. In this case, only the protonation and deprotonation according to the presence of acid or base takes place and is reversible. That means, if a solution is turned acidic, it will give a color, and when you add slowly small amounts of base, it will change into another color. And again when you acidify, that means nothing is lost, it is only a matter of protonation and deprotonation. Acids are proton donors and bases are proton acceptors. The indicator causes the color of the solution to change depending on the pH. So that is the main crux of the whole story of using a natural dye for being into or to be able to be valid for this kind of pH indicator work or business, and must have one very crucial property, and that is indicator or the dye extract or changing the color of the solution must be affected by change in pH. So, what it boils down to, that whatever the dye condition may be of the anthocyanin, there are many types of anthocyanin. The main crux is that once you protonate, that means you add a proton source, and acid is a proton source, it should give a particular color, and when a base is added and the solution becomes basic, it should give another color. That is the main crux of this pH indicator work. And the acid that is added and the base that are added are in only small quantities just to get the coloration. We are not going to dye with this color solution. It is acting only as a pH indicator, and as pH is increased, it should have one color, and as the pH is decreased, it should have another color. That means, when the pH is decreased from 7 towards 0, then it is acidic. When the pH increases from 7 to 14, then it becomes basic. Only then this dye will be considered as a good model for being a candidate for pH indicator. So, that is the only prerequisite. In dyeing, in printing, we had many other requisites. It should have good fabric adherence, it should have good fastness property, the fabric should be able to take the dye, and the dye uptake should be very good, etc., etc. We do not have to worry about that in pH indicator work, because only thing that we have to remember, that it should have a structure which can get affected by proteination and deproteination. So, a pH indicator, what is the nature and what are the uses? pH indicators are themselves acids or bases. A pH indicator is just a weak acid with differently colored acid and conjugate base forms, and it is mainly used as test whether the solution is acidic or basic. pH indicators are frequently employed in titrations in analytical chemistry and biology to determine the extent of chemical reaction. So, as you may recall that we had many pH indicators in BSc class and in MSc class. If you have done any kind of titrometric analysis, then you would have remembered that phenolphthalein and those kind of indicators are just added. Now, phenolphthalein by itself is colorless, but under a particular basic condition it becomes pink, and that appearance of the pink color in a colorless solution indicates that the end point has reached. Therefore, it is considered as a pH indicator. Just like phenolphthalein, even natural dyes can be used, and particularly from the class of anthocyanin. Use of pH indicator. Where all we use this? A pH indicator is just a weak acid with differently colored acid and conjugate base form. When we have any acid, there is a reversible reaction and H plus goes away, and whatever remains is the conjugate base. So, that is what is meant by, if any molecule is protonated at one point of time, the loss of proton will leave behind the unprotonated part in the conjugate base. Uses. Many uses of indicator is to test. The main use of indicator, particularly, there are many uses, but the main use of indicator is to test whether a solution is acidic or basic. With no access of pH meter, we just make use of a simple way to find whether the solution is acidic by dipping the litmus paper. Now, the litmus paper has been coated by a dye which shows change in coloration. With rose anthocyanin can do the same function and act as pH indicator. So, basically what is there on the litmus paper? The litmus paper is also covered with a colorless dye. The moment you put it in an acidic solution, it shows an acidic color. The moment you put that litmus paper in a basic solution, it shows another color, and the deepening of the color goes on to show how concentrated the acid or the base is. So, it is a very simple phenomena. Anthocyanin from red rose petals. The rose anthocyanin actually fits into the requirement of its salient feature and its salient requirements. So, the main use of indicator is to test a solution whether it is acidic or basic. So, suppose if in the laboratory we do not have pH meter, which of course is quite unlikely because it is the smallest equipment that each laboratory has. But in case we do not have, if we are working in the field and if we have anthocyanin solution, we can test that with the help of this anthocyanin. pH indicators are frequently employed in titrations in analytical chemistry and biology to determine the extent of chemical reaction. So, we see that we have this pH and there is a different color that is given on the box and we try to match the color. All of you must have at least come across some time or the other with this litmus paper or pH paper. I am sure that if you have done any experiment in the chemistry laboratory in your masters or bachelors, you would have seen litmus paper or pH paper. How are they made? It is basically a filter paper over which some dye, mostly synthetic dyes, are coated, and these dyes are pH sensitive under wet condition. So, once you dip this pH paper into the solution, it shows the color whether it is acidic, neutral or basic. So, that means that it is just giving a qualitative information whether the solution under test is acidic or basic. It does not give the exact value of the acidity or the basicity. It is a very generic information that is obtained from pH indicators. pH indicators made from synthetic dyes. So, the litmus paper and pH paper actually have synthetic dyes. Another indicator that one uses very popularly in titration in analytical chemistry is the bromothymol blue, which is yellow in color when it is under acidic condition and it turns blue in the basic condition. But there have been some natural sources also from the plant pigments that can act as acid base indicators. So, apart from synthetic dyes which can act as pH indicators, natural dyes, natural pigments also can act as acid base indicator. Whether we call them pH indicator or acid base indicator, it is one and the same. Many fruits, flowers and vegetables contain chemical substances that change color in solution of different pH. Acid or base, natural indicators such as the one which can be obtained from hibiscus flower, turmeric, red cabbage and some other kinds of plants. So, people have explored hibiscus flower which is red in color, gudhal which is an anthocyanin, a turmeric which has lot of conjugated system, red cabbage again is a source of anthocyanin, and many other such sources have been explored as natural sources for indicators for pH. So, we have pH indicator sources both from artificial and natural sources. They have been enlisted here. Many artificial acid base indicators in a chemical laboratory have been in use, which are made from synthetically. Phenolphthalein, it is a colorless solution in acidic medium, pink in basic solution. Bromothymol blue, it is yellow in acidic and blue in basic solution. So, these are some of the artificial pH indicators. From the plant source, plant pigments can act as acid base indicators. Many flowers, fruits and vegetables containing chemical substances particularly belonging to the anthocyanin class of colorants can change color in solution of different pH. Acid or base natural indicators such as hibiscus, turmeric, red cabbage, rose petal are some other kinds of plants that have been used as pH indicators. So, there are many sources which have been explored. Willstatter in 1913 isolated and extensively studied blue and red pigments of flowers. Apples, autumn leaves, roses, strawberries and cranberry juice appeared red. Blueberries, cornflower appear blue. Grapes, blackberries and red cabbage appeared purple. All these colors, due to the presence of cyanidin based color, they also were found out that there is one common anthocyanin, and that is cyanidin, and that is what is responsible for the bright coloration of the red color and the blue color in different acidic and basic medium. So, in way back in 1913, Willstatter found out this, and this was a very basic information that there is a compound which is susceptible for protonation and deprotonation, and that can act as acid base indicator. Among the natural indicators, since we are talking about natural dyes in this lecture, we will keep our focus to natural indicators. Many natural colored compounds can behave as acid base indicators. And we saw a while ago the mention of alizarin, which is 1,2-dihydroxy anthraquinone, is an orange dye present in the root of madder plant. It was used to dye wool in ancient times in Egypt, Persia and India. In an 0.5% alcoholic solution, alizarin is yellow at pH 5.5 and is red at pH 6.8. Cochineal, which is sourced from insect, is an acid base indicator made from the body of dried female cochineal insect found in Mexico and Central America. Curcumin or turmeric is a yellow dye found in curry powder. It turns from yellow at pH 7.4 to red at pH 8.6. And this is a common phenomena. When you take turmeric and you wish, suppose if it has stained your white cloth and you want to wash it, since the soaps are all harshly basic, they will turn that spot, yellow spot into red spot, which will become even worse. So, this is a common thing that it reacts with base. Litmus, esculin, logwood and a very important group of compounds called anthocyanin can act as plant based indicators. Here role of anthocyanin will be discussed with the case of flower Rosa rosa, commonly known as rose. Rose, which is a temple waste, can be collected not only for dye extraction but even can be used as pH indicator. pH indicator from other plants. Alizarin is one member of anthraquinoid dyes, is an orange dye which is present in the root of madder. And as mentioned, people had earlier used for dyeing wool in ancient Egypt, Persia and India. It is a very old dye, and it is also used in traditional Ayurvedic parallel system of medicine, and is about 0.5% its alcoholic solution. Alizarin can show yellow color instead of orange, at 5.5 pH and red color in presence of 6.8. Now you see that the range is very small, 5.5 and 6.8 for the color difference. So, this is where alizaline has a small range. It can be yellow from 5.5 and it can become red at 6.8, even below the neutral. It is all in the acidic region that these two colors appear. Cochineal is an acid base indicator made from the body of the female cochineal insect found in Mexico and Central America. So, even that is found to be a good acid base indicator. And if you remember, the carmicic acid had a structure which could get protonated and deprotonated very easily to act as acid base indicator. Curcumin or turmeric yellow is a natural dye found in curry powders. It turns yellow at pH 7.4, but it turns red at pH 8.6. And rightly so, if you recall, if there is a turmeric mark on your wrist and if you try to wash it with soap which is alkaline, it makes the yellow mark turn into reddish orange shade, and that is what is an acid base indicator all about. But this also has a very small window between the acid and the base. It is acidic and it is yellow at 7.4 pH, whereas when it turns red it is 8.6 pH under the basic condition. Major source therefore for pH indicator is then what it boils down to, anthocyanin. Anthocyanins are versatile and plentiful flavonoid pigments found in red purplish fruits and vegetables, including purple cabbage, beetroot, blueberries, cherries, roseberries and purple grapes. Within the plant, they serve as key antioxidants and pigments contributing to the coloration of the flowers. Anthocyanins occur in all higher plants, mostly in flowers and fruits, but also in leaves, stems and roots in these flowers. They are found predominantly in the outer cell layer, so they are in the cytoplasm. The anthocyanin are water soluble, strong colors and have been used to color food since historical time. So, they are of the food grade. So, they are in the edible category of the natural dyes and they are water soluble, so that makes it more easy for it to be used in acidic solution and in basic solution, because solubility is no issue with anthocyanin. So, anthocyanin have an advantage that they are water soluble, and because they are water soluble, whenever this solution is acidified they will give one color, whenever it is basified it will give another color. Red cabbage also can be a source of pH indicator. We saw alizarin can be a pH indicator, we saw cochineal which can be a pH indicator. So, rose petal also could be an indicator, and likewise there are many plants which can act as indicators, provided they have the capability to get protonated and deprotonated. So, when the acidity changes, the color changes obviously. If it is pH dependent dye, the acidity or the basicity, when it is changing the color of that particular dye at that point of time, will definitely change if a change in pH is brought about. So, because they have this capability of getting protonated, this functionality has come in them inherently. For example, the color of red cabbage is enhanced with the addition of vinegar or any other acid. Vinegar is nothing but the dilute form of acetic acid. When cooked in aluminium pans, which cause a more alkaline environment, the color changes to purple and blue. So, these were indications that anthocyanins are easily pH dependent, and any kind of alteration in the acidity or the basicity of the solution will make a change in the extract. So, it is a very well understood fact, whether it is alizarin, whether it is cochineal, whether it is rose petal, whether it is red cabbage, whether it is beetroot, any natural dye extract from the anthocyanin class or anthocyaninoid class, if it can get protonated easily and deprotonated equally easily, then it is a good candidate for being pH indicator. Hibiscus rosa sinensis, Ipomia fistula, Clitoria ternate can all act as pH indicators because they are from the class of anthocyanin molecules. Flowers, when they are used as indicators, the flowers containing anthocyanin pigments whose color depend on pH, therefore, they can be used as pH indicators easily. This we have understood by now, and this we had discussed earlier also, that anthocyanins have pH sensitivity. Economic use of the pigment of some common flowers as acid alkali indicators has been shown by using common flowers like Hibiscus rosa sinensis, Ipomia fistula, Clitoria ternate, and they all contain anthocyanin molecule. So, all of them are actually anthocyanin based structures. So, what does it go to prove? That anthocyanin by itself is a moiety which can have reversible reaction with H plus when it is added, or H plus when it is subtracted, or it is deprotonated. We do not say it is subtracted or abstracted, but we say it is protonated and deprotonated. The acetone extract of the pigment turn red in presence of acid and show absorbance as to 500 nanometer for Hibiscus rosa sinensis, or at 525 for Ipomia and Clitoria. So, under the acidic condition, they are more on the red tone, and therefore, their wavelength, absorption wavelength, lambda max is in the range of 500 to 525 under acidic condition. Use the rose color as pH indicator, and in a few slides earlier we had discussed that rose petals which can be obtained from temple waste can act as pH indicator. The anthocyanin was extracted from rose flowers by 3 different methods using methanolic solution of 0.1 HCl, citric acid and tartaric acid. So, three different acids were used for the isolation of this anthocyanin, or dissolution I should say. So, the whole idea was to show whether we can take out the colorant more effectively. If you recall, we had shown that rose cyanin, anthocyanin and hibiscus anthocyanin extraction, we had placed 1.1% of HCl method by using replaced the 0.1 HCl method, because HCl is very harsh, by using citric acid. Why? Because we were trying to make the process of dyeing more eco-friendly. Here also we have tried to use 3 different methods for extraction of the dye from anthocyanin from rose flower. So, everywhere we are trying to avoid using HCl because it is a strong corrosive acid. In this case, we took 3 instances. One is using 0.1 normal HCl, second method is citric acid use, and the third method is use of tartaric acid. The anthocyanin was used as a natural indicator in acid base titration. The intrinsic pH of the extract was 2.88, that means it was already quite acidic. So, when the extract, because it is acidified extract, obviously the pH will be fairly low, and it was found to be 2.88 because it was extracted in acid solution, whether it is 0.1 HCl, whether it is citric acid or tartaric acid. So, obviously the pH will already be at 2.88. Rose anthocyanin extract showed wavelength maximum change from 517 nanometer, that is dark pink, to 592 nanometer, which is green, between the pH range of 2 to 9. Now, here you see there is a change which is fairly big. Between 2 to 9 we can use it, and the lambda max were changed from 517 nanometer to 592 nanometer. 517 is in the range of dark pink, whereas 592 becomes green in color. Rose anthocyanin, unlike the other anthocyanins which were showing very small window, 5.5 to 6.8 and that kind of small window, here we have a range from 2 to 9. Rose anthocyanin, the colorant present in the rose flower, is mainly consisting of cyanidin, pelargonium and peonidin, or 2 mixtures of these pigments. So, you see that these 3 main pigments which are participating in the acid base indicator work, and these are all anthocyanin, and the anthocyanins are called cyanidin, pelargonium and peonidin. So, these are the names of the different structure, just the way in anthraquinone or madder dye we saw it had alizarin, purpurine, pseudopurpurine, mangistin and so on. Similarly, rose anthocyanin has cyanidin, pelargonium and peonidin anthocyanins present. In acidic medium, that is the pH 2 to 9, which is in acidic aqueous medium pH ranging from 2 to 9, there are 3 forms of cyanidin: the flavinium cation AH plus, the carbinol B and the quinonoid base A. Equilibrium between the 2 neutral forms occur exclusively by the way of the flavinium cation. So, it is all related to structural details. Flavinium cation is the main, which is protonated anthocyanin pigment. Then there is a carbinol, and then there is a quinoid structure which is in the basic form. And there is a constant equilibrium between all these 3 structures, and they indicate the entire range of pH from 2 to 9. Now, if we look at these structures, cyanidin, pelargonidin and peonidin, you see there is a fairly good amount of similarity. The basic skeletal structure remains the same. That means the functional group and the ring A and B are common. It is only the functional groups which are different on the third ring. Cyanidin has 2 hydroxy group, pelargonine has 1 hydroxy group, and peonidine has 1 hydroxy and 1 methoxy group. That makes them different anthocyanins. How the method of Rose pH indicator was developed? We developed this method in our laboratory, and we are very proud to say that a very convenient method of extraction of anthocyanin from rose flower, that is botanical name is Rosa rosa, has been developed using methanolic solution of 3% citric acid, which gave better yield of anthocyanin than the methanolic solution made from 0.1% of hydrochloric acid. So, one improvement that we showed was the extraction with 3% of citric acid, replacing the earlier described method of using 0.1% of hydrochloric acid. It has been shown that by changing the pH of the extract from 2 to 9, the hue color changes from dark pink to mehndi green. The extract showed wavelength maximum change from 517 nanometer, which is dark pink, to 592 nanometer, which becomes green, between the pH range 2 to 9. Use of anthocyanin extracted from rose flower as natural indicator for acid base titration. So, now it is an established fact that this can be used as an acid base indicator, and it has a very good range from 2 to 9. The intrinsic pH of the extract was 2.88 because it was extracted by 3% of citric acid. Significant changes were observed when stannous salt was added to the rose anthocyanin extract. The spectroscopic data of the extracted anthocyanin pigment indicated a shift in wavelength maxima of the colors by addition of stannous salt, and the complex with a change in pH of the aqueous medium. The usefulness of rose flower as natural acid base indicator has been exemplified for the first time by us. Now, you look at these colors. It is a rose anthocyanin color scale on different pH shows color from pink to green. So, pink is the intrinsic color, which is at 2.88 pH, and then gradually as the pH is increased from 2 to 9, different color shades appear, which can be indicative of the pH that it is corresponding to. So, thus it becomes a very useful method of using the rose anthocyanin extract as pH indicator. When tests were carried out, because see, we have to see the repeatability. So, the homogeneity of rose anthocyanin HCl indicator in acid base titration at different normality. So, if we add 0.1 normal, then 1 normal, 2 normal, does it remain constant by addition of HCl and NaOH? And it did show homogeneity. Now, this is a very, very important fact. Suppose if there was no homogeneity, what would happen? That as we change the normality of the acid and base, they would not the points would not coincide. That means the change would not occur simultaneously and in equilibrium and in equivalence, and that is not a good indicator that it is a good candidate for being called as pH indicator. Therefore, it was required to do this homogeneity test at different normalities of HCl and NaOH when the extract was extracted with HCl. The same experiment was carried out. Homogeneity of rose anthocyanin, which was extracted by citric acid, 3% citric acid, also showed that when the normalities of HCl's were changed and added to the rose extract, it showed that the points coincided very well, which means the acidity and the basicity are at equilibrium, and when one extra drop of acid or one extra drop of base is added, then they shift to the other side. So, this equilibrium, if it is correct, if it is repeatable, then only we can say that it is a good candidate for making pH indicator. Homogeneity of anthocyanin HCl indicator. At the titer value of the HCl extracted rose anthocyanin, we see that we go on there is a homogeneity of anthocyanin HCl indicator in the acid base titration at different normalities. There is no anomaly. At no point addition of higher normal HCl can make any difference. When equivalent amount of the same normality NaOH is added, it is in equilibrium, and the normal NaOH is titered. The change and the changing back of the color is making it a good indicator. Just the way we were able to use anthocyanin, just the way we were able to use phenolphthalein, a synthetic source of indicator, same way we can use this anthocyanin. It was possible to use rose anthocyanin and the change occur from pink to green, and the gradation from going to pink to lighter pink to yellowish to greenish and then to green. And that gradation, whenever there is an acid or base, that is altered. So, with 0.01 normal, with 0.1 normal, then with 1, 2, 3, 4, 5, 6, 7, 8 normal solutions of the acid and base gave consistency in the result. So, that is an indicator that it is having homogeneity. It can be used as pH indicator, and there is no harm in using them. Similar exercise was done to check the homogeneity of the rose anthocyanin extracted by citric acid, and same results were obtained. That means that whether we are using 0.1 normal HCl versus 0.1 normal NaOH, whenever 1 drop is added, the equilibrium shifts to the other side, and when that is added in excess, the equilibrium shifts to the other side. If it is happening at a homogeneity level, that means every time it is going back and forth correctly without showing any anomaly, then we say it is showing homogeneity. In order to be able to prove whether this is a good extract, whether citric acid is creating any problem in its acting as an pH indicator, has been proven that we can definitely use any way extracted solution either with HCl or with citric acid. 3 different types of extraction were carried out. One was with 0.1 normal HCl, second one was with 3% citric acid, and the third extract was done with tartaric acid to get the rose anthocyanin extracted effectively. Ease of making pH indicator with rose petal. Now, having been able to achieve, in conclusion, we can say that the goal of this work was to have a non-textile use of the rose anthocyanin. First purpose was, can we use rose anthocyanin for any other purpose other than textile dyeing and printing? And the answer is yes. Rose anthocyanin can be used as pH indicator very effectively. It is possible to make use of this such as an indicator, and a simple and cheap indicator from the anthocyanin of rose flower, and it was proven and shown that it is possible to make pH indicator out of the rose anthocyanin, whether we extract it with 0.1 normal HCl or with citric acid, which means that both the ways it is very effective for the extraction of the color. The selection of the natural dye to indicate specific pH levels based on their color changes, and we found that it works under the pH range of 2 to 9. So, it has a good range of pH. It can cover from 2 to the other end 9. 2 comes very acidic, whereas 9 is fairly basic, which is a fairly good range of pH. Acidified methanolic extract of Rosa rosa flower were prepared and used as new indicators in the quantitative analysis of standardization of sodium hydroxide and HCl. Because they are standard titration that a person needs to do in the laboratory, in the analytical laboratory, and this was proven by us very effectively. Effectivity of natural pH indicator. So, we do not need to use phenolphthalein or those kind of other synthetic dyes any longer. It replaces phenolphthalein because phenolphthalein is a synthetic pH indicator, and it can be replaced by a natural dye which can be used, and the answer is, can we use a natural dye for using as pH indicator, and the answer is yes. So, we have tried to show that effectively it can be used, such as natural extract from the flowers, particularly from the anthocyanin series, which can be used as very good indicators, and they give quantitative results as compared with the conventional indicators, and the results are in good agreement. And we checked the homogeneity, and we found that it does give very good and consistent result. Because the final aim of finding another use of dye is whether it is fulfilling all the criteria of a good pH indicator. If it is doing so, it is a good candidate to be used as pH indicator. What is the kind of pH range that it can cover is the next answer, because we have seen that in the case of alizarin the window was very small, 5.5 to 6.8, does not serve a big purpose. Whereas, now the question is, if we want to use it as a phenolphthalein or that kind of pH indicator, what is the kind of pH range that these anthocyanin can cover? In case of rose anthocyanin, the pH ranges from 2 to 9, which is a fairly good range if we try to make a comparison with alizarin, where the pH range was only very small, 5.5 to 6.8, or for that matter even cochineal was given very slow small range. When the range is very small, the use becomes limited, but if it has good range, it can be used for acid base titration very easily and can replace phenolphthalein, because the color change also can be noticed. In this case, the color change was so apparent from pink shade to green shade, it gave such a beautiful range of color that one could actually be able to make pH paper out of it. And that exercise is a worthwhile exercise, because there are pH papers available in market, but those are made from synthetic dyes. So, there is a good proposition that even litmus papers can be made now, replacing the synthetic dyes and using rosa extract. The three main structures of the anthocyanins is like this. Under acidic form, this is the situation that it has the halochromic structure. Under acid addition, this is what happens, but when there is a base, equivalent amount of base, then it will form a neutral. So, under acidic form it will be red, then it will go to blue to green under the basic condition. So, what it means is that it is just a matter of protonation and deprotonation that makes all the changes in the structure. Whether we are adding acid or whether we are adding a base can change the structure marginally, making a change in the color. And that is something that we have to remember, that the main role of pH indicator comes from structural differences of protonation and deprotonation. Change in structure of anthocyanins. Acidic conditions maintain the stability of flavinium ion and increase the intensity of the red hue of the anthocyanin pigment. This characteristic makes it a good candidate as a colorant, where the red anthocyanin pigment is highly stable in acidic aqueous solutions. The structure of anthocyanin also changes with the proton concentration, resulting in anthocyanin being reddish at pH 1, blue at pH 2 to 4 and colorless at pH 5 or higher. So, different anthocyanins can show different kind of pH ranges. Anthocyanin molecules will change their color depending upon the pH of their environment. Thus, it may serve as a pH indicator. The anthocyanin turns red pink in acids, which is pH 1 to 6, reddish purple in neutral solutions, which is pH 7, and green in alkaline or basic solution, which is 8 to 14. This is the maximum range, and these are the color that are indicative of the pH changes along with the structural differences by protonation and deprotonation. Natural pH indicators can be prepared just before the experiment. The activity of plant extract Rosa indica or Rubus occidentalis to replace synthetic indicators. Synthetic indicators cause chemical and environmental pollution, are toxic, expensive and rarely available. Methanolic extract of this Rosa indica or Rubus occidentalis exhibits sharp and intense color change in comparison to the standard synthetic indicators like phenolphthalein and methyl orange. Herbal indicators are pollution free, non-toxic, easily available and cost effective. Substitution of the routinely based synthetic indicators can be done successfully by flower extract, as they are simple, less hazardous to human, cost effective, readily available, eco-friendly, accurate and precise, and can be prepared just before the experiment. So, if I have to conclude this, I will say that natural dyes can be used for non-textile purposes. They are extracted for pH indicator work. They are extracted either by 0.1 HCl solution or 3% of citric acid or 3% of tartaric acid, and they show homogeneity over a range of different normality 0.01, 0.1, 1, 2, 3, 4, 5, 6, 7, 8 normal solutions of HCl and NaOH, which means that they have a stable structure both by protonation and deprotonation. There is a stability in the structures and there is a repeatability. Therefore, they can be used as replacement of synthetic pH indicators like phenolphthalein and methyl orange, and natural dyes can now be extended, their use can be extended to make pH indicators. With this, we have come to an end of this lecture. Thank you.